as a speaker, Jianping Li from the Chinese Academy of Science is responsible for the laboratory for geophysical fluid dynamics. So he's going to talk about nonlinear local Lyapunov exponents and applications for predictability. So the floor is yours, please.
Okay, thank you. So good morning, ladies and gentlemen. I'm very glad to be here to give a talk about nonlinear local Lyapunov exponent and its application to predictability study. So this is the outline of my presentation. I will start with a brief introduction and then move on to linear arrow growth dynamics, and then we'll propose a nonlinear local Lyapunov exponent. And by using of this nonlinear method to study atmospheric and oceanic predictability. Also, we employ this method to investigate interdecadal changes of weather potential predictability and the possible causes. And finally, closing remarks. So the prediction of chaotic systems is really challenging problem. The long-term behavior of chaotic systems is essentially unpredictable because of the property of extreme sensitivity to initial errors. However, the deterministic nature of chaotic systems may allow us to some extent to make their prediction in short, limited time. However, you can ask question: how far ahead can we predict the chaotic system? For example, at the atmosphere and the climate system. This is really of practical significant practice. So in order to answer this question, there are two approaches. One is qualitative approaches. For example, signal to noise ratio variance analysis of signal and noisy and lagged correlation analysis. Those methods are basically based on the relative magnitude of external signal and internal noisy. However, those qualitative approaches can only tell us where is possibly lower predictability and where is possibly higher. Cannot tell us any quantitative information about the predictability range. So quantifying the limit of predictability is a major task in the predictability study. Actually, there are several methods in this aspect. The first one, the empirical method, which was initially proposed by Lorentz, the father of chaos. However, it's very hard to find two similar fields. The second one is that dynamical, empirical method. This actually is based on statistical turbulent theory. Actually, this method, makes sense in theory but practical. Those two methods so far, not many people use them to study predictability. The third one, I prefer the third one, the dynamical method, which contains two approaches: numerical experiment, or we can employ some numerical models to study predictability limit. Another one is dynamic system theory. So today I will talk about this one. Firstly, before we propose nonlinear arrow growth dynamics, we should learn some about linear growth arrow growth dynamics. So for n-dimensional dynamic system, you have arrow evolution equation like this. If we remove, this is the linear term, this is the nonlinear term. If we remove the nonlinear term, we can have linear approximation equation, and you can define linear propagator to have a large Lyapunov exponent. The linear arrow growth theory uses this to describe the arrow growth of a nonlinear system. So here is a comparison of this, the result between the linear theory and the real one. We take the Lorentz system as example. Here the dashed line indicates the result from a linear theory, and the solid line is the real arrow growth. Here the mean arrow growth. You can see that at the beginning, the linear, the result from linear theory is consistent with the real one, indicating when the initial arrow is smaller at the beginning, the linear theory can describe the arrow growth. However, with time increases, the result from the linear theory go to the infinite. However, the real one go to the saturation level. So in order to describe this behavior, we should propose nonlinear arrow growth dynamics. Here we must take this nonlinear arrow growth term into account to define nonlinear propagator like this, and then define nonlinear local Lyapunov exponent, which depends on initial states and also initial arrow, the propagation, the magnitude of perturbation, and also it depends on the time interval. If we integrate all initial states over an attractor, we can have ensemble average of nonlinear local Lyapunov exponent, which only depends on the magnitude of initial arrows, and we can use this relative growth of initial arrow to to describe the arrow growth. Firstly, we prove this kind of probability convergence theorem because we think. Okay.
Excuse me. In the figures you showed before,
okay,
on the arrow growth.
Yes.
Yes. In fact, Lorentz and other authors have proposed some kind of logistic curve to describe the arrow evolution.
Yes, you are right. Yeah, you are right. Yes, they already use some as you mentioned that the very simple formula to describe this kind of evolution. But now we want to know for the very complex nonlinear systems, we should know that we use this saturation level. Firstly, we should know if any chaotic systems there is saturation level for arrow growth. Second, we could use this kind of saturation level to define the predictability range. And Lorentz did not study this one. They also propose some very simple formula to describe this kind of arrow growth. Thank you. So assume that the independent random variables xi have the following probability distribution, and we can prove that the product of those xi will be convergent, a constant in probability p. And by using of this theorem, we proved this kind of saturation theorem of mean relative growth of initial arrow. For a chaotic dynamic system, the mean relative growth of initial arrow will necessarily reach a saturation value in a finite time interval. The average predictable limit of a chaotic system could be quantitatively determined as the time at which the mean relative growth of initial arrow reaches its saturation level. That is to say, there exists a time Tp. For any time larger than Tp, this product equals a constant where lambda t is a nonlinear local Lyapunov exponent. The TP is actually the predictability limit, and this theorem provides the approach to quantify the predictability limit of chaotic systems. Here we show example, for example, from the logistic map. This panel shows evolution of mean nonlinear local Lyapunov exponents, and this one shows this arrow growth. Maybe after 40 the unit time, the arrow will reach saturation level. Here, this line is the result from a theoretical saturation level. You can say that the result from theoretical is well agree with this actual saturation level. So we can use this. For example, the limit of dynamical predictability can be defined as the time at which arrow reaches a certain critical, for example, 95% or others of its saturation level.
What I value 95%? Mean that you, in terms of predictability, you can predict something like 5%.
Pardon that?
I mean, when you reach a relative error of 95%,
yeah,
means basically that you are no more able to predict anything except for 5%.
Yeah. So I'm not sure. I'm not. But usually, yeah, you can use any levels. For example, more than. Yeah. So I cannot answer this question. Yeah. So also, for multi-dimensional dynamic systems, we can define multi-dimensional nonlinear local Lyapunov exponents. If the first nonlinear local Lyapunov along the most rapidly growing direction has been obtained, we can define a second rapidly growing direction to get the multi-dimensional nonlinear local Lyapunov exponents. We employ the so-called Graham-Schmidt orthonormalization procedure to get this multi-dimensional nonlinear local Lyapunov exponents. But this is not the focus on this presentation. I will skip them in detail. So before we employ this nonlinear method to estimate the predictability limit of the real system, for example, the atmosphere, the ocean, and the climate, we should introduce the two concepts, practical and potential predictability limits. So before we introduce the two concepts, we should know what does mean saturation level. To answer this question, we should know this kind of concept of attractor radius, which is defined as the average of distance between any two states over an attractor. It can be calculated by this formula. F is the probability distribution. And for the perfect model, for example, the Lorentz model or other typical nonlinear models, the arrow saturation value equals actually this attractor radius. So you can calculate this radius to compare with the numerical result from this model. They are the same. Also, another for the perspective of statistical analysis, there is another important concept, which is standard deviation. Actually, there is a very good relationship between the attractor radius and the standard deviation. Actually, the attractor radius equals the square root of 2 times standard deviation. So we can, in the past, many authors used, standard deviation to estimate predictability. But here we show, theoretical basis for this point. And then we can know about the practical and potential predictability limits. Here is, error growth, and here is, standard deviation, and here is attractor radius. If the practical limit is defined as the time when mean error growth reaches standard deviation, and the potential limit, which is also called a theoretical limit, defined as the time at which the mean growth reaches attractor radius. So in practice, if we use this kind of, because we don't know exactly the equation of atmosphere. Actually, we know the primary the equation of them, but with roughly parameters. We don't know exactly the number of parameters. So but we want to know the predictability range of real atmosphere. So how to solve this problem? Because we have a long-term observation data. So one idea is we could use those kind of data, which are the solutions of the equation, to calculate the nonlinear local Lyapunov exponent, and then to estimate the predictability range of the real system. Here we propose local dynamic analog. So here we take initial distance and evolutionary distance both into account to find a very good local dynamical analog. If before we only take this initial distance into account. However, this kind of method cannot guarantee that we can find the real analog. For example, there's 3 points. The B and the C are both close to the point A. However, even the B is closer than C. However, the B is not analog point. If we use this kind of initial distance, we may find that the B is the analog of A. However, we must take evolutionary distance into account. In a short interval, we may exclude B but include C. So I think this is very, very important. We can use this procedure to find good analog by using long-term observation data. So here is the example. The result from Lorenz's 63 model. The red line means mean growth, error growth from this kind of local dynamical analog oscillator, and the blue line is theoretical growth from the error growth equations. You can see that this oscillator can have very good performance to give the evolution of error growth. Valerie.
Could you repeat how you estimate the mean error growth with the LDA algorithm?
Yes, for this model, we can integrate this model to get the long-term numerical results, which we are regarded as observation, right? We use those kind of long-term time series to find this LDA and to get the error growth. And this one because we know the equation, exactly equation of the Lorentz, and we input the error perturbation into the equation to get the real error perturbation, the growth from the equations, and we can make a comparison with it. So that means if we don't know exactly the equation of the nonlinear system, we can still use the observations of the system to get this kind of error, mean error growth. Here is the result for the slightly more complex Lorentz 96 model. Once again, you have the better result from this LDE method. Now we directly go to the applications. We may use this kind of algorithm to study the predictability limit of the atmosphere at the various time scales. For example, here is the spatial distribution of the annual mean practical predictability limit of a daily 500 millibar gel potential high. The left panel from NSAP NCAR real analysis data, and the right one from the actually NSAP CFSV2 daily forecasts, and the middle one is the zonal mean profiles of the practical predicted limit from the observation and from model respectively. This panel, you can see that you have largest predictability over tropics with around 2 weeks, right? 2 weeks, and you have still 2 centers over the both polar regions, north and south polar regions.
So can you explain what is plotted exactly? So the colors means day of predictability.
Yes, the color, the shading means the daily predictability.
And how do you compute this?
Okay, sorry, just now I mentioned it. Yeah, yes, very good question. Because we have a lot of observation data, right? We should use this time series to find the good local dynamical analog to get the error growth, and if we may find the saturation level, if we can get the predictability limit range.
You find sets of trajectory that are analogs in the sense you define, and then you look at the error growth between this trajectory.
In each point.
At every point. Yeah. You see, yes. For example, we actually at the equator here we have the long-term time series, right? And we can, find the analog to get the error growth.
What is the reference state you get? Because basically you compare locally the evolution of the geopotential height with the analogs. So when one day the geopotential height is 1000 hectopascal, and then you study the evolution of the days when it is 999 hectopascal, or what?
Yes, here we only consider the geopotential height at the 500 millibar.
Yes.
Yes. Also, we don't only consider, we may take the small regions into account, not only this point, to get the the weather regime, similar weather regimes. Okay.
One more question. These analog trajectories, how close do they get to the reference set? I mean, can you quantify this in relation to something like the attractor radius of the model, or?
Yeah. Now here our point is we only use observation data to calculate. Because we don't know exactly formulation of the equations, right? Because those parameters, are not well defined. We don't know exactly the formula. So we but we have the long-term solutions of the equation, the systems. For example, observation data. Yes, please.
How can you be sure that you have good analogs?
Yes, good question. Actually, yeah, very good question. Here we showed, we use this kind of K-error divergence to guarantee this, to answer this question. If we must have the enough numbers of the observation data. For example, this shows the how many data we need to calculate this LDA.
Yeah, but, usually the analogs are defined in the full phase space.
Yes.
So locally, when you project locally, you could have situations that are globally not the same at all. So locally, you will have some.
No, here we use locally,
Yeah, but
not global.
okay, but how can you say that this is a good analog locally?
Yeah, for the real system, we cannot answer this question. However, for the system which the controlling equations are known, we may know these methods are available. Right? Yeah, you are right. That's why we use this algorithm to the real system. But here, for Lorentz model, you can see that the result quite good so far. Yeah. So you have the very lower predictability range over middle latitudes. In this reason, you have very strong because of strong clinical properties. You have the very strong Wesleys over this region, and also strong storm track there. So you have lower predictability range. Actually, less than 12 days, something. So if we take a look at the model, actually the model, can so far has not, very good predictability. For example, especially in tropics, in real atmosphere, you have the largest predictability in tropics. However, model has very poor, performance for predicting, the tropical weather. That means, there is a very large room for model to improve their, improve their quality to increase the predictability. Or, for example, we can, improve the physical parameterizations to improve the model to have the good performance. So we can also, use this method to study the predictability range of the monthly and the seasonal, which are the short-term climate. For monthly, this one, the left panel shows the global distribution of annual mean practical, predictability range for monthly, seasonal, and the right one for potential monthly and seasonal zonal mean profiles respectively. And you have the also largest predictability range over tropics, implying the tropics is the most important source of predictability for seasonal or short-term climate prediction. If we take a look at the predictability range of sea surface temperature, here is the special distribution of annual mean. practical, and potential predictability limits of monthly SST surfaces, sea surface temperature from hardline SST. You have, maximum, predictability range over Eastern Tropical Pacific, which actually reflects the ENSO phenomenon. ENSO actually is, most important source of predictability range. If we take a look at the potential predictability of SST, you may have another source of predictability limit over high latitude, for example, North Atlantic Ocean and southern ocean, right? And that means if we make seasonal forecast for the atmosphere, we may take the ocean. We may also take the ocean over the high latitude into account. So actually, the predictability range varies with season. Here is the global distribution of the predictability limit of monthly SST for 4 seasons: spring, summer, autumn, and winter. Right? So you have different the predictable limit difference from the different seasons. We may now we may only take focus on the El Nino region because that is important external forcing for the atmosphere. Here, the seasonal variation of SST anomaly mean predictability limit in different regions. Actually, in the Nino region, which contains 4 parts: Nino 1+2, Nino 3, Nino 4, and Nino 3.4. You can see that you have the lowest predictability range in winter, right? What does this mean? So if we take a look at this details, the predictability limit of Nino 3 SST anomalous for 4 seasons. So for spring, you have the 12 months of predictability limit. Summer around 10, and autumn around 7 months. However, the winter very low, no more than 6 months. That means there is a very famous phenomenon, the spring predictability barrier problem in SSTA of the tropical middle and eastern Pacific. Actually, this kind of a nonlinear method also can tell us this kind of spring predictability barrier, because if you have initial state in winter, the prediction we cannot make the prediction go beyond the 2 seasons. So I think the all right predictions will stop at next spring, which is called spring barrier problem. If we move on, if we take a look at other regions, for example, the tropical ocean, you have another predictability barrier. For example, the winter predictability barrier, because you have a minimal predictability limit in autumn here. Autumn. So another question is, because predictability is controlled by multi-forcing, so we should separately investigate the effect of each forcing factor on predictability. We propose conditional nonlinear local exponent to study this question. For example, ENSO is one of the primary boundary forcing for the monthly and seasonal predictability of the atmosphere. And we can define this kind of conditional nonlinear local exponent to study the conditional predictability of the atmosphere associated with ENSO. So here is the result. The distributions of the annual means, practical and potential predictability limits of monthly 500 millibar gel potential height explained by ENSO component. You can see that over tropicals, the large variance of predictability limit can be explained by ENSO. And over middle high latitude, especially for this over this region, North Pacific and South Pacific, the ENSO is still the mean source of predictability limit over these regions. That means if we make climate prediction over those regions, we must take the ENSO into account. So now move on to the interdecadal changes of weather potential predictability, WPP, and the possible causes. So we know the predictability varies with time. So here, is some result for the interdecadal changes of weather potential predictability. Actually, those 5 panels shows anomalies of the weather potential predictability limit of 500 millibar height in different decades relative to the this period average. So you can see that the weather predictability varies with decades. For example, the Eastern Tropical Pacific, the weather predictability over this region before the 1970s, they are very relatively lower, and after that becomes strong, higher. Over this middle high latitude of northern hemisphere, the predictability limit before this 1970s, you have higher predictability limit over this region. However, after this decade, they becomes lower. This panel shows can show this point clearly. This is the linear trend coefficients of the weather potential predictability of gel potential height at 500 millibar for this period. You can see that the predictability over this region will be going up, and the over middle highlight of northern hemisphere become lower, and the southern hemisphere middle high latitude going up. So this is zonal average of linear trend coefficients. You have positive trend over middle high latitude of southern hemisphere and tropical region, and negative over most parts of northern hemisphere and the Antarctic region. That means over those regions, the predictability limit will decreases. So what are responsible for this kind of decadal changes of atmospheric predictability? We answer this question from the 2 aspects. Over, in middle high latitude, we should consider atmospheric stability, which reflects the dynamics of the atmospheric internal variability. In tropics, we should take a thermal process into account. For example, the SST over tropicals is most important external forcing, thermal forcing for the atmosphere. So here is the linear trend coefficients of the difference between surface and the 500 millibar annual mean temperature for this period. You can see that over most part of the northern hemisphere, the atmosphere, the difference between the surface and the middle troposphere temperature increases. Means the atmospheric condition becomes more unstable. As a result, you have decrease in predictability limit over those regions, right? And you have the difference between the surface and the middle troposphere temperature decrease over middle latitude of southern hemisphere. As a result, you have increase in predictability limit. because atmospheric conditions over these regions, become more stable. However, over in the tropics, because during last, I didn't show this picture about the status of the SST in the tropics. In the last 3 decades, the temperature, the SST surface temperature over this region, going down. That means the cooling. There is a large La Nina type of phenomenon over this region. That means the atmosphere should be become stable over this region. Then you have increase in predictability limit over tropics. So I basically finished my presentation. Come to concluding remarks. We introduced the nonlinear error growth dynamics and present the nonlinear local Lyapunov exponent to quantitatively study predictability limit, and we propose an algorithm which allows us to search for the local dynamical analogous is present to estimate the nonlinear local Lyapunov exponent from the observation data. Use this method, we performed a quantitative analysis on temperature spatial distribution of the predictability limit of the atmosphere at various time scales. And we know from those results that the tropics is the main source of predictability. Also, there is a big room for model to improve their performance. And also, the ENSO is a very, very important external forcing of source of atmosphere predictability. During last 6 decades, the predictability limit, weather predictability limit, there is interdecadal change in weather predictability limit, and the over most part of northern hemisphere, the atmosphere becomes more unstable. Then we have a decrease in predictability limit over the northern hemisphere. However, we have the opposite case in the southern hemisphere. So further work is required to examine broader applications of the nonlinear local Lyapunov exponent method in predictability studies of atmosphere, ocean, and other systems. Especially, we can employ this method to study ensemble forecast and target observation. So I think that's all. Thank you. You can learn more about this method from website to download some papers. Okay, thank you.
Thank you. So, do we have comments or questions?
Okay.
There.
Thank you.
You have defined the time scale of saturation of the error, TP, you mentioned there.
Yeah.
And well, what is did you look at the link between this value of saturation and the typical time scale associated with the dominant Lyapunov exponent, so the inverse of the dominant Lyapunov exponent? Did you look at that, or?
Yes, actually, we already looked this at this point. If we for the larger time scale, we have a longer predictability limit, and the smaller local Lyapunov exponent, and vice versa.
The smaller Lyapunov exponents, you know?
Yes, if for the longer time scale. Yeah, the larger time scale, the smaller.
The larger time scale of predictability, you mean?
No, the large scale, the phenomenon. If we take, for example, we study the monthly time scale, and the local Lyapunov exponent for this monthly is smaller than that of weather daily. Yeah.
Then,
Initially, when you define the nonlinear local Lyapunov exponent, you explained that it was depending also on the initial error delta.
Yes.
And then you didn't talk about this anymore.
Yes, that's a very, very good question. Yeah, here when we use this method to study the atmosphere, the predictability of the atmosphere, we at the first step we should estimate the mean magnitude of error, initial error. So which depends on observations for how to explain? Depends on the observational instruments. For example, if we measure the temperature, the minimum error almost equals to the 0.1 something. We can estimate this magnitude by using of the time series. For example, we can compare the difference between any 2 points, and we get the for example, let me. For example, this is the observation time series, and we can calculate the errors between any, right? And we found some errors which belong to the smaller size. For example, yes, we can order this error. For example, and we choose some examples and to make average of this error to estimate the basically estimate this initial error.
Let me ask you a simpler question, maybe. So, for this Lorentz model here,
Yeah.
does the blue curve depends on the initial error you use or not? Does it depend much on the initial error you use?
Actually, for individual one, it depends on initial errors. But here we integrate, this error growth for all, initial states.
no, but the size of the error, I think that's
Sure,
The size of the
sure.
Yes.
You say that the blue curve does not depend much on the size of the error.
No, it depends on. Yeah, here, we for this one, for the Lorentz model, if we want to get the blue one, we should define the initial perturbation first. For example, any integration should be yeah.
the curve will change. That the blue curve will change if you change.
Yes. Yes, you're right.
So because
Yeah.
the time t equals 0,
Yes.
this is not 0.
Yeah. Let me explain this.
Jumping,
Yeah.
at the time equals 0, that is not 0, right? It's finite.
Yes, it's not 0. It's yes, exactly. Yeah. So let me introduce this, explain this point. Yeah, here.
It's finite, yes.
Actually, the saturation level depends on perturbation. Different perturbation, you have a different, saturation level, right? If I draw the picture, for example, we have the different perturbation level.
the curve will shift to the right, basically. If you go to smaller and smaller delta zero, the blue curve should go to the right.
Yes.
Basically. And in the limit of delta zero becoming infinitesimal, of course, you get the linear growth. The growth of, like for the linear perturbation. If delta zero is infinitesimal, your approximation with linear growth is as good, is better.
Not exactly, but you know, if the perturbation go to the zero, we have infinite predictability limit.
Yes, because it never reaches a finite
Yes.
time.
Yes.
At finite time. Yes.
Yeah.
Okay. Yes.
Yeah, the smaller the predictation, the larger predictability limit.
Other comments?
That's why we, for the weather forecast, we should improve our the quality of the initial states, right?
Comments and questions? I had one question on the use you made on the relationship between models and the reanalysis. So what your data seem to show that the models do an extremely poor job as weather predictors near the tropics. Is that correct? At 500 hectopascal. So forward.
Yeah.
Here. So
Yeah.
it seems to say, well, models behave well. If I believe in this estimator, I would say models behave well in the extratropics. The patterns are also quite similar.
Yeah.
Whereas in the tropics, they just are not able to predict at all.
You are a very good question. So to answer this question, we should know, there are several reasons for this point. Over middle high latitude, I think there are two aspects. One, we have some, more observation data over this region actually, compared to the tropics, because our ocean covers the tropics. We have not much more observation data there. Second one, because we in the past in the last 100 year we paid attention to the theoretical dynamic theory over the middle latitudes is good, right? So I think physical parameterizations in model can be well over this middle high latitude. However, compared to northern hemisphere, you have lower, relative lower predictability limit over middle latitude of southern hemisphere. Well, on the one hand, we have not many observation data compared to northern hemisphere, right? So on the other hand, for the southern hemisphere, you have a stronger storm track compared to the northern hemisphere. So that's why you have a relatively lower predictive limit over. Yeah.
But in the tropics, there are, I think, 4 days.
Yeah. But in the tropics, actually,
your predictive scale is really low.
Very, very low, because we don't know much about the thermal properties of the atmosphere. Even the convection. Convection over the tropics is very, very complex. So far, we have not enough knowledge about the convection, even convection parameters in the model.
So lack of knowledge of the states of the atmosphere, or lack of knowledge of dynamical processes?
I think both. Yeah, I think both. So I'm sorry, I have to stop here because I will catch my coach, 12:20 something.
Yes.
I'm sorry.
Okay, thank you very, very much. So I think we stop here.
Thank you. Yeah.